This is a summary of Jack Parker Holder's PhD thesis. We already mentioned a few words yesterday. Today we want to do a formal summary. Why is this important? Why are we talking about somebody's PhD thesis here? Well, we think that the path towards real-world intelligence is going to be paved through actually simulating artificial worlds in which agents can learn. And that's for almost obvious reasons, I hope. You can't have robots or cars, drones, or any kind of real world thing, any kind of metal go around the real world learning how to behave. It's just difficult. On top of that, once we crack the path of open-ended learning, as I think the technical term is now sort of cementing itself, once we crack that path and we understand how that works and how we get models to work and things like that, I think we will also get to kind of levels of intelligence that we can't even imagine today. So this is not just about having open-ended real-world type learning so we can get a robot to fold our shirts. This is about having real inverse design solutions for material science. This is understanding particle physics in a whole different way. This is, maybe building starships on a weekly basis that improve by orders of magnitude every time they get launched, because we have new insights into physics, new insights into nature. This is what I think. This is the North Star here. I think Jack's PhD thesis just fits all of this. That's why we discuss it. I don't have a particular stake here in any which way. I don't know the person. I'm not a fan of DeepMind or anything like that, so I'm not promoting anybody here. It just happens to be a piece of work that is relevant to our thinking, and that's why we discuss it. So we're going to discuss the thesis and also look a little bit forward and where we see the world of AI going, just as a prelude summary, open-ended, continuous learning. That is, so take Jack Parker Holder's idea, take Genie, take augmented video learning, and then add the Richard Sutton continuous learning idea to this. And I think we're kind of getting a good picture of where this is going. This is not even on podcast. It's September 10th. 2025, this is Krim Delco. For the day, we're up 2.9%. The market's up 50 basis points. For the year, we're down 4.2%. The market is up 11. We're underperforming by 15.2%. So let's start with the thesis. So the idea is open-ended learning. So Jack's thesis is structured in the following way. So he starts with reinforcement learning as the overarching algorithmic idea. So what does that mean? We want to have an agent that adapts to the environment and learns from the environment. Now, reinforcement learning itself can be rigid or can be open. In other words, you can have fixed parameters and say, okay, here's learn with these parameters, like the learning rate, the trade-off between exploration and exploitation. These things can be hand coded, or they can be adaptive. So what Jack does, he goes from rigid RL to automated RL, right? So now we have an agent that adjusts its own parameters as it goes. Always keep in mind there's an overarching goal that it follows. Or to use something that way back I've heard Sergey Levin say, we want to have some sort of Robinson Crusoe robot that just wakes up on an island somewhere and figures out how it actually should be moving around the environment. So auto RL, first step. But then we have the problem of the environment, right? In other words, well, we have one environment that this thing can be learning on. Now, in principle, we can just have many, handcrafted environments that we have this thing learn on, which of course is not scalable. What we want is a scalable solution. We want a solution that can learn on its own at scale with only compute, or actually eventually only energy as a scaling factor. So how do we get that? Well, we start with the unsupervised environment design, which is UED. So that's really the fundamental idea here, and that's where also Genie comes out of at the end. In other words, we want to create an environment that is in an unsupervised way adapting and changing. Now, there's a couple of steps that Jack is using here. He's also using some information theoretic approaches. Fundamentally, what he's trying to do is he's trying to show in principle that the way this should be working is that we want to have very high diversity in environments, but then high certainty within the environments, which means that we can reduce epistemic uncertainty. What that means is, in plain English, we want the agent to explore many different types of environments, but within the exploration space. So whenever the agent is in an environment, it should be pretty clear what it should be doing, right? So if I work on, if my robot is trained to walk on sand and then ice and then water, those are different environments, but within the environment, it should be very quickly approaching towards some sort of solution where it gets high rewards. In other words, it should be able to learn within the environment pretty quickly. And we shouldn't expose the agent to environments where it can't learn. So for example, simulate the black hole is not going to help because we have no clue how we don't even know what a black hole is. It's not really useful. So we want to bring environments to bear where the agent actually can learn very quickly, but the environment should be very diverse. So that is high information value, and that's kind of the information theoretic backbone, which I just thought is interesting. He then goes on to the world model idea. So what is a world model? It is just really, think about it like a general way to describe unsupervised environment design, or another word for it, basically. So we create different world models. We create different models of the environment dynamically. Now, how that can be done, I mean, that's, obviously, eventually that is what Genie is becoming. So how do we create world models? Let's say randomly. I mean, randomness is always a good start, right? But we could also maybe find better algorithms to create those world models. So that's, that there's that. I don't want to go into details of how to do this. I think this is actually an open-ended problem anyway. It's by any means solved. But I want to mention a few things within this context, and the most important one is we're learning from video. NVIDIA yesterday at the AI Infra conference in Santa Clara made an announcement, Rubin CPX. It's a 1 million token context window video generation model. Why is NVIDIA doing this? Well, a couple of reasons. I think this is the beauty of investing in AI. There are all these milestones that can be met and money can be made on the path towards the big goal. So NVIDIA wants, of course, video gamers to have better video experiences. That is one use case that is monetizable very quickly. NVIDIA probably wants eventually to offer Hollywood the opportunity to change even movie sections in a generative way. Now that is maybe open, but at least one thing a director could do is start with a sequence and then have the AI generate different types of endings, that kind of thing. So that's one use case. But eventually where NVIDIA is going is we want to create these types of augmented artificial worlds, or many worlds, as we call it, in which agents can learn, because real-world AI is the North Star of NVIDIA. As Jensen has said many times, that's where the amount of data and the amount of learning actually really exponentially goes higher, and therefore also the company's relevance goes up. So this is highly related actually to this presentation by Jack Parker-Holder, because he is also talking about video learning in different contexts, but he's using, in one of the presentations, links in the show note, he's talking about a world model that Wave has learned, that is a London-based autonomous driving company, and we can extrapolate to Tesla. So Tesla has learned a world model of driving, and it's done that by just collecting millions and millions of videos of real world driving. We could use that to prompt this type of augmented video learning agent that then creates its own worlds and therefore creates different world models on which the agent then can learn. So this is the North Star. And now imagine this for Optimus. So imagine now we have other types of robots. We have humanoid robots, drones, and we have nanorobots in human bodies. We have all kinds of different robots. Who knows where this is going, right? The point is we have agents, so we have embodied AIs that do work in the real world, and they are trained in simulation by an open-ended learning process. This is the key. This is the North Star. And the way we see this going is now we can add Richard Sutton's continuous learning paradigm to it. So imagine you have the ability to create many simulator worlds that then form world models in which the agent can learn. So the agent can, in principle, continuously be learning. So this paradigm of batch training, fine-tuning, and then test time can be compressed into a continuous learning approach in simulation. And then we have the sim to real problem, and then we have the application. So we could have, like, let's say, a world where every day the agent just downloads its latest version, or every hour, every 10 minutes, I don't know, whatever. I mean, that's a engineering / entrepreneurial answer to a problem. But in principle, you could have an agent like this. And this is really, really exciting. And that's where we see all this conversation about AGI, superintelligence. It's not that important to us, but we see definitely a path towards a much, much more effective intelligence than what we have today. Whether it's superintelligence, whether it's better than humans or so, it's not that relevant. In certain areas, it's going to be much better than humans. In other areas, maybe not so, but that remains to be seen. Now, to finish this conversation and maybe to give a little bit of, how should I say, outlook of where we see this going. The most exciting thing for us here at Launch Capital Partners is, there's two exciting things. One is real world robotics. So again, it's cars, humanoids, drones, nanorobots, fixing materials, nanorobots, adjusting the Starship heat tiles in action in real time. This is open-ended. But what we really think also is possible here is that we can actually learn physics much better. And we can do that literally the way nature is doing it. We create many worlds, and then within those many worlds, we have agents learning how to act within those many worlds. And then whatever explanations and solutions the agent comes up with, which are hard to vary, which kind of sustain themselves through time, those are the kinds of solutions that we will actually apply in our real world. So this is the North Star. We can get better physics, we can get better natural sciences. As far as social sciences is concerned and stuff, I think I want to stay away from that for now, but definitely on the natural side, we can learn from experience by generating real worlds which are embedded in, generating artificial worlds which are embedded in the real world and composable. So they remember when we change the world on them, and they learn, they remember the context, and they actually really learn how to behave and don't just sort of adapt, kind of like that guy in Memento. So they have some memory, and they remember actions and things along those lines. So that's kind of the way we see it. I think, again, it's Jack Parker Holder's idea of having an open-ended environment in which the agent can learn in simulation through syntactic worlds. And then we have the continuous learning approach by Richard Sutton. I think this combination is really going to get us very tangible, very quickly to a much, much more intelligent world. Now, As far as infrastructure is concerned, this will require a lot more data and a lot more energy investments, which of course is part of our investment thesis, and this sort of ties the whole thing together for people who wonder, why are we talking about all this? The podcast, Not Even Wrong podcast's purpose is to give people a sense for what it feels like to run a hedge fund. Understanding where the science is going, understanding where the tech is going, helps you understand where the future is going to be as far as investment and capex is concerned. We are going to be compute and energy constrained, so invest in compute and energy, and also invest in companies that actually understand this paradigm, such as, for example, Tesla, and also you can see a tangible monetization in the near future. Thank you.